Hello everybody, we're going to move on to a new set of notes now. We're going to be dealing with entropy and free energy. I'm going to introduce some ideas dealing with entropy tonight, just to get us going. This is a shorter note set, but I would argue a very important one conceptually. So in the discussion of entropy, the first thing to clear up is what we mean by spontaneous and non-spontaneous. And I'm on, this would be my note sets called entropy and free energy. And so a spontaneous process something that's spontaneous occurs without an outside driving force, meaning you don't have to do work for it to occur. You don't have to do work. So for example, let's say we have a system. We have two bulbs attached together with some kind of a stopper here. And let's, for the sake of argument, say that it's all at a constant temperature T. Make the system, make the argument a little clear. One of the things that you observe, let's say you have gas molecules over here. And let's say this is a vacuum. It has no gas or a lot less gas than the other side. It could even be a lower pressure system. And we open this stopper. Well, we know what's going to happen from observation, that you're going to have a movement of gas from one side to the other spontaneously. There's no work done in this process. And so there's no work done on the system in this process to have this occur. And so that's an example. And you can think about mechanical processes. If you drop a ball, it spontaneously goes down. If you want to pick the ball up, you have to bend down and do work to get it. If we want to force these gas molecules back to the other side, if we want them to force them back over here, we could do that. We'd have to do work to do that. So the spontaneous process occurs naturally without an outside driving force. An easy way of thinking of it is you do not have to do work on the system for it to occur. Spontaneity, something being spontaneous or showing spontaneity, is not equal to it being fast or having speed. This term has nothing really to do with speed. Now, that would probably be a very fast process unless it was a little tiny leak. But there's certain processes that occur spontaneously. For example, diamond. I'll draw it as like a diamond type of thing. It has a little diamond structure. I'm not good at drawing. You have a diamond, and what you'll see is that at room temperature, it actually has a driving force in nature to want it goes to spontaneously form graphite, which I'm not going to attempt to draw, but graphite is, you'll see it, observe it as like a powder on a molecular level. It looks like chicken wire sheets of carbon. So, if you have a diamond ring, you're not observing it turn to graphite in real time, but it has a direction. So spontaneity really deals with wanting to go in a direction. Okay, as I say here, the term spontaneous is a thermodynamic term associated with direction. And so speed is something else. That is a process that might, to get going, take billions of years to see any appreciable change. On the other hand, you can have certain chemical reactions that are spontaneous, that are fast, but they're not terms that speed, and anything dealing with speed is under the category of kinetics. There are links between these two things, but they are different as well. Spontaneity, something being spontaneous or non-spontaneous, is under the dogma of thermodynamics. I'll just call it thermo so I don't have to write the whole thing out. So that's, that would be an example. Another example is that if you have glucose, sugar, let's make glucose, let's make a table sugar. Table sugar, sucrose. It spontaneously wants to go to carbon dioxide and water. That's a spontaneous process at room temperature. But if you have some table sugar sitting out, you don't spontaneously see it catch a fire and form CO2 and water. And the analogy to that would be glucose. Glucose in the body inevitably has a driving force to head towards CO2. But if you didn't have the enzymes, getting back to last chapter, to facilitate it moving on a biological time scale, we would die, animals would die, and so forth. So the glucose spontaneously, similar to table sugar, glucose does spontaneously want to go to carbon dioxide and water, but it's too slow. So that's the thing, is that you have spontaneity, it's a direction it doesn't want to go there. That's thermo. The speed of how you get there is we're under the regime of kinetics. I have to get my eraser, which is a kitchen napkin here. Forgot to bring one over. So now, similarly, when we say something's non-spontaneous or non-spontaneity, if we're talking about it, how we want to say the terminology. So if something's not spontaneous, I'm never sure if it has a in my notes I have it with hyphens and not, so why not do it here? I'll do it both ways. I'm not sure. I may cover both bases in terms of what's correct. If something's non-spontaneous, it does not mean that it will never, it's impossible. It's not equal to saying it's impossible. It's just saying if you want it to go, you're going to have to do work or have a driving force to make it go. For example, let's go back to the case where we have the system where it's well mixed, and we've got everything's at the same temperature T both sides, and you got gas molecules on both sides. And if you want to get it to the condition where you have few or none on this side, you can do that. You can pull a vacuum and do some sort of somehow remove them and put them on the other side. That is doable, but you're going to have to do work in that process in order to do this. You're going to have some kind of trick that's going to involve expenditure of energy to make that happen. And so, similarly, like we talked about osmotic pressure, that's diffusion driven, right? So you had diffusion of water, but we could do work on a system by applying pressure to it to stop the osmotic flow. We're basically hindering the diffusion of water in that case, which is spontaneous, by application of pressure, doing work. And so you can think of it that way, and there's numerous examples you can think of. And so one of the things we have a tendency to do as in science is we tend to, I don't want to say overestimate, but we place a lot of emphasis early on energy. And certainly thermodynamics is largely a study of energy. But let's think about this. We've studied a couple different energies. We studied internal energy. I teach it with the symbol U. I think that's how everybody at UVM, University of Vermont, teaches it. Other schools might use a different symbol, but U is very widely used. And then there's H, which is almost universally used for enthalpy. Those are two types of energy. They're related because H is defined as U plus PV. Enthalpy is basically subtracting out, it's a minus of a minus PV, basically, when you go through taking the changes in what this is. You can show that delta H is equal to QP, heat under constant pressure, because you basically are subtracting out the work associated with pressure volume changes in the system. And we often use H for descriptions of breaking bonds and reactions and so forth to get that extra term of forming or having gases come in to the system or being formed with the volume changes associated with that. Enthalpy is getting rid of that contribution. But the point is, these are both terms for energy. Now, I'm going to do a little digression here. This goes back to last semester. Probably just touched on and not emphasized, but I'm going to emphasize it now. I'm going to give an example. For an ideal, meaning it behaves by PV equals nRT, gas, follows the ideal gas law. And I'm taking the case where it's atomic, just to keep it simple, what they call technically monatomic. Something like helium gas under ambient conditions behaves to all practical purposes. Ideally, it's monatomic, means it's atomic gas. It can be shown, I'm not going to prove this in this course, that the internal energy of the system, as well as the enthalpy, they're both proportional to, on a molar scale, RT. For a monatomic gas, it's precisely U is equal to 3 seconds RT on molar scaling in terms of energy. And enthalpy is 5 seconds RT, but again, enthalpy is also proportional to RT. That's the big point. There is no other terms like that come in to do with pressure or anything else. So if we look at delta H or delta U, we get processes that are proportional to the changes in temperatures. Meaning, when you do a process with an ideal monatomic gas that is isothermal, meaning you do it with the same temperature, delta T is equal to 0. That does not mean T is equal to 0. It means the change in temperature is 0. It means delta U and delta H are equal to 0. There's no change in internal energy. There's no change in the enthalpy. Well, does that mean that processes that are isothermal for ideal monatomic gases, let's take the simplest case, under isothermal conditions do not occur? Well, if you set up an experiment, you can do this in any lab anywhere, is again, repeat the experiment before. Have a stopcock here, have the temperature be the same on both sides, have gases here, open up, gases will go to the other side. This is a process in which delta U is going to be equal to 0. There's no change in temperature. So when you have the gases spread out, it's not this is not driven, and delta H is going to be 0 as well. This is not driven by energy. It's driven by something else. So you have many processes where you cannot rationalize the spontaneity of the process by strictly energy. You have to take something else into account. And so, as a matter of fact, what I'm going to introduce foundationally is the driving force of spontaneity. We just make ways of linking it to energy, which I'll explain. It's a nuance that we have to develop this a little further to understand. But the point is that you can have a process, for example, expansion of an ideal gas isothermally, just taking a monatomic as an equation of that, that's spontaneous all day long, isothermally, and there is no energetic contribution. So there's other examples I talk about in notes, and we'll talk more about them as we go along. So this introduces the idea of entropy. Entropy is typically denoted by S, and I'm going to define it as I do in the notes. I'm going to just call it S. It's a thermostate function, and this definition is on page 2, and so I'm going to abbreviate things. It's a thermodynamic state function. So we can write deltas for it, right? We can't do that with heat and work. That really shouldn't be a comma there, bad grammar. Increases with the number of energetically equivalent, let's write equal, ways to arrange components. And the components I'm using this term very broadly. It's actually not limited to atoms and molecules and ions in chemistry. It's a very broad entity. We're going to focus on thermodynamic entropy pertaining to chemistry, so it will be atoms and molecules, but it could be other things as well, of a system to achieve a particular state. So let's think about this. Entropy is a thermodynamic state function that increases with the number of energetically equal ways to arrange components of a system to achieve a particular state. It's a hell of a statement. So let me give an example. One of the things you do need to do if you're rusty on state function, go back and read the thermo notes, which were basically I forgot what chapter it was, 9 or 10ish in there. Where we talk about state functions, because that's an important concept. I've done this example before, but I'm going to do it again because it's an important idea. Let's have a box. I'm going to do something really simple here. Again, the math here I'll say is FYI. The concept's what's important. We've done this before. I just want to do it again. We put two balls in here. The grids are the same. No matter what the grid, the way they're configured, it'll be the same energy. The balls will not carry any more weight if it's in this box. This box. The balls are identical. They're identical and indistinguishable, and we want to think of all the different combinations we can have. The math for this is again goes by what's called the binomial coefficient. You do not need to know this, FYI. I just need to do the math for myself. It's 4 factorial, 4 minus 2 factorial, and then the smaller number 2 factorial. It's called the binomial coefficient. This ends up being 4 times 3 times 2 times 1. Those are factorials. 2 times 1 is 2. 2 times 1 is 2. I don't know why I'm writing two symbols here. 2 times 1 is 2. So this gives us 4 down here. That cancels out, and that leaves that 4 canceled. This is 6. And I want to make just a little, not too much more complicated system. This is 6, and let's put 2 balls in here. Like this, and so the same type of thing. How many different ways? This one would be harder to mix them all around. This would be 6 factorial over, let's see here, 6 minus 2 is 4 factorial, 2 factorial, which is 6 times 5 times, don't want to forget that, 5 times 4 factorial. I'm going to leave it there. We got the 4 factorial and the 2 factorial is 2. 4 factorial cancels this. This is 30 divided by 2, 15. Check my math, or you can go through and count it out manually. So 6 and 15. This will be a higher entropy system than this. We can call what we just did, we could define these binomial coefficients for this particular process as I'll just use the symbol W to be in accord with the book. It's a way of counting all the different ways, if you will. You want to think of W as ways. A lot of times it's abbreviated omega. It's often called in statistical books the statistical weight. It's also called the multiplicity, particularly in physics books. But in chemistry, we use the term multiplicity for other things, so I'm going to avoid that term. It's a perfectly good term. Now, for mathematical reasons related to thermo, this does link to the idea of entropy. The problem with it is, and I'm just going to say this if you're interested, I've written a whole a note set on it for another course. You just ask me for it and I'll send it. The problem with the weight, W, is that it doesn't scale as an intensive or extensive thermodynamic variable. So what we do, and to have a cohesive set of math associated with thermo, we want to have something that we can make extensive or intensive, like a good state function should be. And if you don't remember what those terms mean, you want to go back and look at the notes from early in the semester. I think it's right in the chemistry notes because I use those terms all the time. To me, they're foundational in science. Let's see here. So S, to be scaled correctly, is going to be proportional to the ln of W, the weight, the statistical weight. And this is proportionality again. To make it the statistical thermodynamics for chemistry and physics, we can put a constant in front of it. I'll put 2. Unfortunately, we use another K. Again, I'm going to put a K sub B here just to denote it as different than the rate constant K. I think it notes I just use a K, but we just did kinetics. So this KB is the what I'm calling here is the Boltzmann constant. And I'll write the number in a second. I just want to finish the equation. ln of W, if you want to do it per number, this is in joules per Kelvin. It's 1.3806 times 10 to the minus 23 joules per Kelvin. I might have it to more or less sig figs in the notes, but that's the big point. We can. This is good when you're dealing with numbers of things, like you say there's 85 particles or there's 1,000,000 particles. You know, that's when. But chemists, so physicists use this all the time. It's perfectly good. We can also use it with molar scaling. I'm just going to denote everything with an S. I'm not going to put any kind of symbology on it. Just say this would be in molar form. This is the gas constant, 8.314 joules per mole Kelvin. So this is in a molar scaling, and this is in a number. When I teach higher level courses, I start out like a physicist. I start out with a few particles, and I do very fundamental things with math, and then I switch, because I'm getting paid by the chemistry department, I switch to chemistry mode, and I put things on a molar scale. I say, let's make it molar now. So a lot of times it's easy to derive things with this, but both of these formulas here, both of these formulas, which are on page 2 of the notes, are called the statistical definition of entropy. I'll just call entropy S. And so we can take that as a fundamental relationship. The fact of the matter is, for this course here, we will not use that equation for a lot of calculations. We probably won't use it at all, but it's good to know for other courses if you go on, particularly in physics. And when I teach thermo, from a chemistry orientation, I actually divert this into another formula. This is strictly FYI. I put it in the form of something like S is proportional to a sum of probability, ln of probability. I put it in another form. I'm leaving off some of the constants and so forth. I put it in terms of probabilities. We won't use that either. But we're going to do work with it in terms of a state function with delta S's, with some very convenient forms for specialized problems. So this was an intro to thermo. This stuff with the math here you don't have to know, but just know those are statistical forms of entropy. And you can see as W goes up, the ln of W is going to go up, and S is going to go up in either equation. So on that note, I'll let you go. It's been a long video, but this is an important concept. So take care.